Hey guys, Mr. Riz here to help you with the 10.1. We're going to be looking at operations with matrices. So our goals here is, how can we interpret matrices and operate them with matrices? So we want to make sure we can add, subtract, and do scalar multiplications with matrices. So first, we're going to kind of jump into an abstract thought here, but we're going to talk about, how we can represent matrices. So let's look at this example here. We have two t-shirts for sale, or we have a stock of them, right? We have this blue t-shirt here, and we can see how many small, medium, larges, and extra larges we have. We also have a red shirt over here, and we can see how many small, medium, larges, and extra large. If we want to construct like a table of those, we can do that pretty easily. Let's go ahead and get my pen here. We could just make, a table for the red and another table for the blue. I'm going to do this out of order. Getting a little colorblind, but the red one's here, and we can make a small, medium, large, extra large. And see, red, we would have like 11, 45, 25, and 28. And then in the blue, we would have 23, 53, 21, and 32. So right here, we constructed a table that represents where we know that each row is the color and each column is the size category. So we could figure out the total of the red, we could figure out the total of the blue, we could figure out the total of the larges that we have and go through and represent. But we have a table here that can go through. Well, what we just did was create a matrix. So matrix is a table or a list of numbers put together with some constraint. So where we kind of understand what the rows and columns represent. So we can look at like, okay, what if we have this matrix here of 5, 3, 0, 2, 1, 4. All right, we could maybe say that this matrix might help us organize some information about more shirts, like we have shirts and sweaters, and we can have small, medium, large sizes. So you can see like in this example here, we'd have like 5 small shirts and 1 medium sweater. We'd have 0 large shirts and we'd have 4 sweaters. And so we can represent numbers in their spots. We don't have to have descriptions of each one of those, but we can look at a chart to represent. Okay, so this is how we can refer to an entire matrix or the elements of a matrix. So typically we call a matrix by a capital letter, and so we have A. So we could call this matrix A or just A. A specific let's say that again. A specific element can be referred to as the subscripts to indicate the row and column where the item is located. So in general, we say like A sub IJ, and so that would be A, matrix A, row I, column J. So if we looked at here, here's our rows, here's row I, here's column J, that's in that spot. So typically though, we use actual numbers. We won't do any abstract things where we don't know how many rows or how many columns we could have. But we could go through and represent, okay, in this column here, A32, A sub 32 would be matrix A, row 3, column 2, which would be an 8. Okay. Now, when it comes to scalar multiplication, it's actually really easy. So say we have this cool thread store, we're looking at clothes again, and they have this matrix C to represent the price of all of their clothes. Okay, so the column here represents the vintage, casual, and distressed. So we have their college, and then we have jeans and jackets. So we can see, the price of those, which is actually crazy expensive, but I'm not into fashion at all, I guess. So if we want to find the sales tax of 5% on every one of those items, what we can do is just simply multiply the matrix C by 5% or 0.05. Now to do scalar multiplication, what we have to do is then to multiply every single element by that same number. Okay, so we can write out like so. We could take S times 0.05, or the sale price or sales tax equals 0.05 times C. So we multiply every single element by 0.05, and so that just changes every single number by the same degree. Okay, so let's try to do this here in this example. You can pause it, try it on your own. We got another one here. We're going to see what the sales tax is, and we're going to find the sales tax for each item. So go ahead, pause, see if you guys can do this correctly. All right, let's see if you did this right. So what we need to do is to multiply every single one of these numbers by 0.06. And so we would get a new column here, a new matrix. If we take 75 times it by 0.06. I'm going to use a calculator here. 75 times 0.06, we get 4.5. 40 times 0.06 is 2.4. 25 times 0.06 is 1.5. 100 times 0.06 is 6. 60 times 0.06 is 3.6. And 30 times 0.06 is 1.8. And there we go. We have a new matrix C where the elements represent the change of each element that it corresponds to. Pretty easy, pretty simple. Now, when it comes to adding or subtracting matrices, all we're going to do is add corresponding elements. So if we have matrix A, which is like this one here of the March sales, and matrix B is April, and we want to add them two matrices together to figure out the total lot, all we have to do is look at the corresponding elements. So we're not going to take like 14 and add it to 11. We're going to add 14 to its corresponding value here, 18. And 28 corresponds with 25 over here. So we match up its corresponding elements and we add them together. All right, so let's look at these two matrices here. Matrix C, what is matrix C? M plus N. Okay, so let's look at this. Matrix C, M plus N. All right, so if we start out with a 2 by 2 matrix, our answer is going to be a 2 by 2. So if we add those together, we'd have -3 plus 6, that's 3. 5 plus 5 is 10. And 2 plus -8 is -6. And 0 plus 0.02 is 0.2. All right, next we'll look at N plus M. All right, so if we did 6 plus -3, that is 3. 5 plus 5 is 10. -2 plus 2 is -6. And 0.02 plus 0 is 0.02. Okay, so here, addition doesn't matter. If we have matrix A plus matrix B, that's the exact same thing as matrix B plus matrix A. What we have to watch out for is with subtraction. So if we have M minus N, we're going to take matrix M and subtract the element of matrix N. So -3 minus 6 is -9. 5 minus 5 is 0. 2 minus -8 is 10. And 0 minus -2 is -0.2. All right. But if we did N minus M, that matrix here, we're going to take the N elements and subtract the M. So 6 minus -3 is 9. 5 minus 5 is 0. -8 minus 2 is -10. And 0.2 minus 0 is 0.2. So you can see these are not the same. And so we have to understand this property, kind of like math. If we can add two things together, they equal the same value if we switch, but not the same thing with subtraction. Okay, so what we're going to do is, we've got to consider how we can add or subtract matrices. The one thing that we have to look at with matrices is that we can't just always add every single matrix C to every other matrix C. If we look at this matrix C here, we would say that this matrix C is a 2 by 3 matrix C because it has 2 rows and 3 columns. Matrix B, though, is a 3 by 2 matrix C because there's 3 rows with 2 columns. All right, you cannot combine or add matrix A to matrix B. The elements have to correspond. If I look at this element here, this element would be A sub row 1 element 3. If I go to B, is there a B row 1 element 3? No, there is not. So we cannot add A and B together. You can see here we can add A to C and A to D. In fact, we can combine them all except for B cannot be added to any of those. Okay, so here's just a review of just some of the key concepts about matrices here, is that we name the dimensions by how many rows and columns there are, and that's how we itemize each element. If we're going to multiply by a scalar, all we need to do is to just distribute or multiply everything together. And when it comes to adding, we add each corresponding element, and same thing with subtracting. All right. So that's pretty much it to matrices. It's really simple. It's going to get a little bit more complicated when we start multiplying and dividing, but we'll start it slow with adding and subtracting. All right, guys, have a good one. We'll see you next time.